Good morning, everyone. Today we are going to start our new topic, that is compression member. We know that in any structure there are beam, column, slab, footing are the our elements of the structure. But in steel structure there are compression member, that is column, tension member, beam. These are the structural elements. In that case, we have studied about the tension member. Now we are going to understand about the compression member. So what is compression member? That we know it is a column, because column is compressed due to load coming from the beam and upward pressure acting at the foundation. So this member is compressed. Even in truss, in transmission line tower, in bridges, and other structures having compression member. So we have to understand about the compression member. What is the compression member and how we can design the compression member using codal criteria. So a structural member which subjected to axial compressive force is known as compression member. There are two main type of compression member, column and struts. Pure vertical member is compression member. When a compression member is oriented vertically, it is known as column. A compression member which may be oriented in any direction and has sufficient bending is called a struts. Means smaller member having smaller cross section area and direction of orientation is any, that is called struts. Compression member are named directly in the different situation as follow: struts, column, tension, post. These are the compression member. Generally, column and struts are identified in our structure. Column and struts are termed as a short column and long column depending upon their position of buckling. So, which are the factors affecting the load carrying capacity of long column? Slenderness ratio. Higher slenderness ratio, lesser the load carrying capacity. Material strength, shape of the cross section. I section is preferred over the equivalent channel section. Eccentricity of load, initial curvature. It reduces the column capacity. And the residual stresses are also there. Means whenever we are going to design, we are ignoring the long column. It must slenderness ratio between short column and the longer column. We know that in our previous subjects, structural analysis 1, in that case, we have understand about the column and struts. And We know that what is a longer column, what is a short column. We have studied in SA1. For the short column and for the long column, Euler's have given us different equations for the position of buckling. Whenever the column is long, it can be buckled, and due to that buckling, there are the four cases is generated as per the end conditions. So Euler's theory for the long column, that is PE is equal to pi square EI upon L square. This equation is studied by us, where P is Euler's buckling load, KL is equal to effective length of the column, and I, that we know, AR square, right? So here we are going to put that equation in this. What we will get, PE upon A is equal to pi square E upon KL upon R whole square. Now the force and the capacity of this, that is 250. So whenever we are going to put all the data over here, FA is equal to 250 megapascal, E is equal to 2 into 10 raised to 5. This is the axial compressive buckling stress, right? So we will get KL upon R, that is 88.6. So KL upon R is less than 88.6, that is short column, and greater than 88.6, that is long column. So from here we can identify the short column and a long column. This is our slenderness ratio, KL upon R must be between these values. So Euler formula is acceptable for the KL upon R is greater than 88.6. So as we discussed, Euler's formula is specifically for the buckling of column, and buckling is done only in long column. So whenever we are going to design a compression member, we have this much choice for the selection of the section. In that case, single angle, double angle, T section, C section, I section, circular hollow pipes, square hollow pipes, rectangular hollow pipes. This is our built up column with 4 angle and the laced. This is our laced column. This is also laced column. These are all are the built up section. I section with 2 plates, built up I section, built up column, I section with channel. These are the different shape of column, and that we can use as a compression member for the designing of the structure. Single angle section are used as a compression member in lightly loaded trusses and towers. As you know, it is short, maybe it is short, or else whenever the compression load are very much small, so we are going to provide smaller section. In that case, we are going to put the single angle section. Equal angle section may be economical than the unequal angle section because their least radius of gyration value are greater for the some area of steel. This thing is clearly identified and understood by us during the examples. So just keeping in mind the least radius of gyration. Double angle bolted or welded back to back are normally used at top and bottom chord of the trusses. In case of double angle unequal angle sections, which longer leg back to back give the better balance between R value about y and z axis that we know. If roof trusses are welded, structural T section may be used for the top chord of the member. Such members will eliminate in cassette plate in highly loaded truss since the web members can be directly welded on the stem of the truss. Single channel are rarely used due to negligible R value about their web axis. Four angles arranged in each other corners, the square are used to corner booms. Circular hollow sections are used as a compression member and bracing member, the tubular trusses, space frame, and offshore platform legs. Now, what is the effective length? That we know. We had studied that effective length in SA1 we have four cases, that is depending on the end condition of the column. The column end conditions and the effective length: first, both end pin; second, both end fix, one end fixed and another hinge; one end is fixed and another is free, that we have studied in Euler's formula. And previously, these are the our cases: both end hinge, then buckling of the column is something like this, and the effective length L is equal to L. Here the both ends are fixed, so buckling somewhere from here to here, so LE is equal to L by 2. Here it is bending something from here, so effective length LE is equal to L by root 2, and it is cantilever column, so L is equal to 2L. The buckling of this column is something like this. So from this we will get the effective length, which is very much useful for the designing of column for a long column and fail due to buckling, so it is very much important. Effective length, that is KL, we know that L is equal to actual length, means unsupported length of the column. K is equal to effective length ratio or effective length coefficient, means it is effective length upon unsupported length, right? The theoretical value of the effective length for the different end conditions are both end pin, then L is equal to L, both end fixed, and L is equal to L by 2. One end fixed and another end hinge, then L is equal to L by root 2. And one end fixed and another is free, that is LE upon 2L. These are the values for this some standard case. But still we have some value that is given on page number 45, ISO 800 2007. In that case, we have the whole table and they have given us for the different end condition what is the effective length for the column. It given. In plate in the joint may fail in tension through the weakness section of the hole. The hole may be arranged in the longitudinal direction in the plate so that the number of holes equals to 2 rows across the width of the heart. That it is a bolted connection. This is our table that is given us the effective length of the column. Here both end restricted means it is fixed and it is free, then 2L. Here this is rotational means roller and it is, but it is something like free, so it is a 2L. Restrain free means it is pin, then it is 1L. As we discussed, they all given in previously, this is the same, but this is actually language of code. Restrain, free and restrain, then it is 1.2L. restrain and free, 0.8 L. All the restraint means fixed, then 0.65 L, right? So, major and minor axis buckling, the major axis buckling, and minor axis buckling. ZZ is the major axis, YY is the minor axis. We know that as shown in the figure, the column has been supported laterally braced C in the direction that braced is perpendicular to the wick of the axis and the cross section. Hence, the wick axis is standard, and hence weak axis Y is useful for us. If the column is to buckle about the y-axis, means major axis, then KL is equal to L by 2. If the column is buckle minor axis, then KL is equal to L. This is our actual scenario, major and minor axis. So, whenever the column going to buckle, it is the buckling from the minor axis. So, we have to first identify major and minor axis, and that is depending on the radius of gyration. And that radius of gyration we have in a steel table. But whenever we are going to take built up section, then it must be found by us. Short column and intermediate compression member. Short, long, and intermediate. Short compression member. For a short compression member, KL upon R is less than 88.86 for FY 250. Failure stress equal to the yield stress. No buckling will occur. It has no practical application. Long column member KL upon R is greater than axial buckling stresses below the proportional limit. They will buckle elastically. Euler's formula gives the strength of the long column. Intermediate length compression member. For the intermediate length of compression member, some fibers may be used to have yield and some fibers will be elastic. These members fail both yielding and the buckling of their behavior, so it should be inelastic. Failure modes. How the column can fail. The possible failure modes in axially loaded columns are given below. First one is local buckling, means the axis may be bent. Failure occur local buckling on one or more individual plates element, that is a flange or wave, with no overall deflection in the deflection normal to the applied load. Failure by local buckling can be prevented by the selecting suitable B by T ratio in components of plates. Overall flexure buckling, that we know just in Euler's. This type of failure, the fail is excessive deflection in the plane of weaker axis. This mode failure normally controlled the design of the most compression member. Squashing. When the length of the column is relatively too small and the column is stocky and the component plates are prevented from the local buckling, then the column will be able to attain the full strength or squash load before failure. Squash load is equal to yield stress into the cross sectional area. This is the strength of axially loaded column. The slenderness compression member is failed somewhere over here. Then tension member, it is when this is stocky and squash load may be taken by him. Which are the cross section and how we can classify that? For that we have used page number 18 in IS 800. Plastic section, we have four failure pattern. First one is plastic, second one is compact, semi-compact, and the slender. Slender we are ignoring because slender column cannot take compressive force. Here, first one is plastic. The cross section which develop the plastic hinge and have rotation capacity required to failure the structure and the foundation of a plastic mechanism. The B by T ratio of the plate element shall be less than that the specified values under the class that given in IS 800 page number 18. Second one is compact cross section which can develop the plastic moment of resistance but have independent the plastic hinge rotation capacity because the local buckling. Semi compact, the cross section in which the extreme fiber is compression can reach the yield stress but cannot develop the plastic moment of resistance due to local buckling. And slender, the cross section in which the element buckle locally even before the reaches yielding stress. These are the capacity. This is the plastic section, this is compact, this is semi compact, and this is slender. Slender having small value of moment capacity. And this is the table in which what we are going to do. This table gives us the total value of the class 1 plastic, compact, semi-compact, and these are our section, and how we will use that clearly identify in our examples. Now here they have given us the knots. This is very much important. It is also given in the code page number 18. These are the section that given page number 19 and how we will use the B and D and H, all the data of particular section that given over here, and this is used in finding out the our class. Thank you. Some important things still required to understand. It will be continued in our next lecture. Thank you.